This research paper presents a novel approach to constructing Riemannian metrics on exotic spheres in 7 dimensions using Kaluza-Klein techniques. The authors apply an inverse Kaluza-Klein procedure to obtain explicit coordinate expressions for metrics on 2 homeomorphic but not diffeomorphic spheres in 7 dimensions. Specifically, they identify Milnor's bundles, among which 10 out of the 14 exotic 7 spheres appear, with non-principal bundles having homogeneous fibers. The authors then develop a general ansatz for the coordinate expression of a metric on the total space of any Milnor's bundle. This ansatz is given in terms of a metric on S4, a metric on S3, which can smoothly vary throughout S4, and a connection on the principal SO4 bundle over S4. As a concrete example, they present explicit formulae for such metrics for the ordinary sphere and the Gromel-Meyer exotic sphere. The paper then performs a non-abelian Kaluza-Klein reduction to gravity in 7 dimensions, according to a slightly simplified version of the metric ansatz above. This reduction yields the standard 4-dimensional Einstein-Yang-Mills system, for which the authors find solutions associated with the geometries of the ordinary sphere and the exotic one. The 2 solutions differ by the winding numbers of the instantons involved. The paper's formalism is based on conventions and basic notions, including principal and associated bundles, and the general expression for the metric on the total space. The authors also provide a detailed analysis of Milnor's bundles, including their representation as associated bundles, the coset space SO4, SO3, and the change of basis. Furthermore, the paper discusses the recovery of the ordinary S7 trivial case, obtaining the same metric with the formalism of 1. The authors also explore the non-trivial case of Milnor's bundles, including the usual sphere and the double instanton. Finally, the paper concludes by discussing the traces of exoticness in 4 dimensions and outlining potential future work. The construction of exotic spheres by Milnor is a significant result in modern differential geometry. These 7-dimensional spaces are homeomorphic but not diffeomorphic to S7. Motivated by their role in theoretical physics, particularly in general relativity and Yang-Mills instantons, their study is crucial for understanding the topological characterization of physical theories. Despite their importance, exotic spheres have received limited attention in the physics literature, especially in the context of string theory. This work aims to bridge this gap by providing a general expression for a natural metric on exotic spheres, focusing on the Gromel-Meyer sphere. The metric is constructed using physics-inspired techniques, generalizing the metric on S7 viewed as the Hopf bundle. The resulting metric is then used for a standard non-abelian Kaluza-Klein reduction of Einstein theory in 7 dimensions, yielding solutions with both the geometry of the standard 7 sphere and the Gromel-Meyer exotic sphere. The construction of exotic spheres is outlined, emphasizing Milnor's work and its relevance to the physics context. The research discusses the properties of the bundle defined by quaternion multiplication, focusing on the total space for specific values of h and L. For h plus L equals 1, the total space EH, L is homeomorphic to S7, with some spaces being exotic manifolds. The authors also explore the subgroups SU, 2, L and SU, 2, R, which are not disjoint, and their relation to the Lie algebras SO4. They introduce 2 bases for SO4, one splitting rotations and boosts, and another illustrating the Lie algebra isomorphism between SO4 and SU2, circled plus SU2. The quotient spaces associated with these subgroups are discussed, including SO4, SO3, asymptotically equal S3 and SO4, SU2, L, R asymptotically equal SO3. The section concludes by outlining the geometrical setting and main results from 1, including the general expression for the metric on a bundle with homogeneous fiber. Let's start with the Lie group G and its subgroup H. We consider the coset space X equals G, H, where we define a basis, T, of the Lie algebra G of G. The indices spanning the Lie subalgebra H of H are denoted as I, J, equals 1, dim, H. For the remaining indices, spanning the complementary space B equals G minus H, we use alpha, beta. A key property is that the coset space is reductive, implying C alpha J equals 0, always satisfied if is compact. The research paper discusses the construction of the round metric on S7 through an inverse Kaluza-Klein process. It begins by defining the metric component as a function of fiber coordinates, allowing for smooth variation from fiber to fiber. The authors then review the construction of the round metric on S7 viewed as a principal bundle via an inverse Kaluza-Klein process, using right-invariant objects instead of left-invariant ones. This involves expressing the line element in terms of Euler angles and decomposing the Maurer-Cartan form. The paper also discusses the gauge potential for the k equals -1 SU, 2, instanton centered at the origin, which is valued in SU, 2. The authors then construct a metric on the total space by choosing the Vielbein on the fiber to be another set of right-invariant 1 forms. This results in the usual round metric on S7. The paper concludes by discussing the moduli of the instanton, including the center and size, and how these can be trivialized. The authors also provide an alternative description of the right-invariant 1 forms using Euler angles, which they find more natural for their formalism. We begin by discussing the choice of G micro nu and a micro for a specific instanton, which leads to the recovery of the line element. This formalism serves as a starting point for generalizing the case of principal bundles. We then consider Milnor's bundles as total spaces of bundles with homogeneous fibers, focusing on the metric for bundles of type 0, 1, and -1, 2. The transition functions are defined, and their equivalence to those in Milnor's construction is demonstrated. The associated fiber bundle is discussed, highlighting its similarity to the principal bundle in terms of transition functions. The coset space SO, 4, SO, 3 is introduced, with its natural basis and algebra satisfying the reductive condition. The keys in K alpha, S are computed, showing their non-trivial nature. This setting is special due to the homogeneous space being a Lie group. The results are compared to those in the literature, and a change of basis is proposed to achieve a more suitable description for exotic spheres. In the context of a geometric approach to the study of the moduli space of monopoles, this research paper explores the relationship between two distinct bases for the tangent space at a given point in the moduli space. The first basis, introduced in section 6.2, is derived from the left and right invariant vector fields on the unit 3 sphere, while the second basis, discussed in section 6.3, arises from the 't-Hooft and anti-Hooft symbols. The connection between these two bases is established through the matrix M, which transforms the first set of vector fields into the second set. This transformation also applies to the dual 1 forms, resulting in a new set of 1 forms that are half the norm of those in the original basis. The paper highlights the significance of the Hopf map, which defines the Hopf fibration S⁻1 right pointing arrow S cubed right pointing arrow S squared, and its realization in the context of the left and right invariant bases. The components of the dual 1 forms in the new basis are given by equations 6.20, with the norm of the 1 forms being half the norm of those in the original basis. This setup is then related to the formalism of 2, with a few subtle differences noted. The transformation matrix M is crucial for understanding the relationship between the two bases, as it allows for the conversion of quantities from one basis to another. The matrix M is also used to find the components of the dual 1 forms in the new basis, which are essential for the geometric analysis of the moduli space. Furthermore, the paper emphasizes the importance of the Hopf map and its role in the fibration S⁻1 right pointing arrow S cubed right pointing arrow S squared, which is realized in the context of the left and right invariant bases. Overall, this research paper provides a detailed examination of the geometric structure of the moduli space of monopoles, focusing on the relationship between two distinct bases for the tangent space at a given point. The transformation matrix M plays a central role in connecting these bases, enabling the conversion of quantities and facilitating the analysis of the moduli space in the context of the geometric approach. The paper discusses the construction of an exotic sphere, a non-standard sphere in differential geometry, using gauge theory and instantons. It begins by outlining the metric on the total space of the Milnor's bundle, which is a particular type of sphere bundle. This metric is composed of two parts: a base part, given by the metric on S⁻4, and a fiber part, which involves the gauge field strength and the curvature of the base. The base metric is chosen to be the standard metric on S⁻4, while the fiber metric is determined by the gauge field strength and the curvature of the base. The authors then describe the gauge field for an anti-instanton and a double instanton, both of which are essential components in constructing the exotic sphere. The anti-instanton gauge field is given by equation 6.27, and the double instanton gauge field is given by equation 6.28. These gauge fields correspond to Milnor's bundle with transition maps having winding numbers 2, 1, thus resulting in an exotic sphere. To make the construction fully explicit, the authors provide the matrix key alpha, which is obtained by choosing the Euler angles as described in the appendix. This matrix is presented in equation 6.29. The paper concludes with a discussion on how these components come together to form the metric on the total space of the Milnor's bundle, which is an exotic sphere. The research discusses the application of a bundle Riemannian metric on the Grommel-Mayer sphere, generalizing the metric from 2. It highlights the simplicity of this bundle metric and its limitations, mentioning the possibility of generalizing the choice of the metric on the base S4, the fiber S3, and the gauge fields. The authors then describe how this metric can be used in a physical theory, specifically in a four-dimensional theory by substituting the metric ansatz into the action of seven-dimensional gravity. They present an instance of how two geometries associated with inequivalent differentiable structures might appear as solutions to a physical theory. The dimensional reduction yields the Einstein-Yang-Mills action with a cosmological constant, agreeing with analogous cases examined in 37 and 31. The dynamics of the theory is described by the standard equations of this system. The authors also discuss the variation of the action with respect to the metric and the gauge fields, using the Bogomolny bound shortcut. They conclude by noting the consistency of their results with scaling the generators by a factor of 1/2 compared to previous sections. The research paper discusses the construction of metrics on Milnor's bundles, inspired by Kaluza-Klein theories, and their dimensional reduction to four-dimensional Einstein-Yang-Mills theory. It focuses on the most relevant example, the seventh sphere, and its exotic versions with inequivalent differentiable structures. The authors derive explicit metrics for these spaces and apply dimensional reduction to obtain solutions in 4 dimensions. The key finding is that inequivalent differentiable structures in 7 dimensions descend to different solutions in the 4-dimensional theory. The paper also highlights the importance of studying the properties of K equals 2 instantons for further applications in physics, such as extending this work to finding exotic sphere solutions in 7D supergravity or constructing Freund-Rubin-like solutions to 11D supergravity. The authors emphasize the simplicity of the metrics derived and their natural occurrence in the context of Kaluza-Klein formalism. The summary begins with acknowledgments to key contributors, including Professor David Berman, Guglielmo Tarallo, and Dr. Mattia Cesaro, for their support and discussions. The research was funded by the Science and Technology Facilities Council, STFC. It then delves into the geometrical objects, specifically reviewing left and right invariant vector fields and the Maurer-Cartan forms on S3 asymptotically equals SU2. The discussion includes the global and local descriptions of these forms, highlighting their significance in the context of diffeomorphism between S3 and SU2. The summary also details the vector fields dual to these forms, their properties, and their roles in generating translations. It concludes with the metric on the unit sphere, demonstrating how the forms can be used to construct it. Throughout, the text maintains a technical and professional tone, ensuring the accuracy and depth required for expert audiences. The paper discusses the dual vector fields to the curvature 2 forms omega A and omega A, which are essential in understanding the geometry of the instanton moduli space. The dual vector fields V1, V2, and V3 for omega A are given by equations A.15, while the dual vector fields V1, V2, and V3 for omega A are presented in equation A.16. These expressions allow for the calculation of the matrix key alpha in coordinates, connecting the two sets of vector fields. In the context of the K equals 1 instanton with unit size centered at the origin, the connection in regular gauge is expressed as A micro equals x squared plus 1, 1/2, eta a micro nu x nu, where eta a micro nu is the t Hooft symbol and x micro are stereographic coordinates on S4. This expression can be transformed into angular coordinates using the stereographic projection maps psi-n and psi-s, defined in equations A.18 and A.19, respectively. The coordinates used by 2 can be read off from the metric 5.1 and are a mixture of standard spherical coordinates and Euler angles, as shown in equation A.20. The Fubini study metric, given in equation A.22, is derived using the parameterization of quaternions chi in terms of chi, micro, u, and v, as seen in equation A.23. The quaternions u and v satisfy uu equals vv equals 1 and are used to express the metric in a more familiar form, as shown in equation A.25. This form highlights the geometry of the instanton moduli space and demonstrates the insensitivity of the metric to the choice of labels on the coordinates, thus providing an explicit isomorphism between S3 and SU2, as discussed in section A.1. The paper discusses the geometry and physics of exotic spheres, focusing on their implications for Kaluza-Klein theories and supergravity. It begins by defining right invariant 1 forms, which are crucial in understanding the curvature and geometry of these spaces. The metric in equation A.27 is introduced, leading to the result in equation A.28, which describes the compactification of D equals 11 supergravity on an exotic S-7. This result is then connected to previous work on supergravity and string theory, including references to large N-field theories, ADS, CFT correspondence, and Einstein metrics on spheres. The paper also explores the relationship between exotic spheres and curvature, referencing various mathematical studies on the subject. It highlights the significance of exotic spheres in dimensions 7, 11, and 15, as well as their role in breaking n equals 8 supergravity down to n equals 1. Furthermore, it touches upon the importance of squashed, stretched, and warped geometries in the context of ADS 4, CFT 3. In addition, the paper provides a comprehensive list of references, covering topics such as higher dimensional unification, Riemannian geometry, and Einstein spaces. These references include works by prominent researchers in the field, such as Percacci and Ranjbar-Damy, Castellani, Romans, and Warner, among others. Overall, the paper offers a detailed analysis of exotic spheres within the framework of Kaluza-Klein theories and supergravity, shedding light on their implications for our understanding of geometry, curvature, and compactification in high-dimensional theories. The pages under consideration delve into the realm of differential geometry, particularly focusing on exotic spheres and their implications for physics. They cite various works that explore these concepts, including references to papers by Derdzinski and Regas, 24, Duran, 25, and Sampietro et al., 39. These studies revolve around the construction of exotic spheres, which are topological spheres that cannot be embedded in Euclidean space with a smooth Riemannian metric of positive curvature. The authors also touch upon the subject of gauge theories, specifically mentioning the work of Jacques et al., 35, Actor, 36, and Duff et al., 37. This discussion is relevant to the context of Yang-Mills instantons, which are solutions to the Yang-Mills equations in four-dimensional spacetime. These instantons have been explored in various contexts, such as gravitational instantons, 38, and their relationship to diffeomorphisms, 39. Moreover, the text references papers on Hamiltonian reduction of geodesic motion on SU3 to SU3, SU2, 40, and solutions to Yang-Mills theory in four-dimensional de Sitter space, 41. These studies demonstrate how geometric and topological concepts can be applied to understand physical phenomena, especially in the context of gauge theories and gravity. In addition, the pages include discussions on self-dual solutions to Euclidean gravity, 42, and instantons, 43. These topics are crucial for understanding the interplay between geometry, topology, and physics, particularly in the context of higher dimensional unifications of gravity and gauge theories, 31. The overall theme of these pages is the exploration of geometric and topological structures, their implications for physics, and their applications in gauge theories and gravity. The references provided offer a comprehensive overview of the relevant literature in this field, highlighting key concepts, methodologies, and findings.